Have you ever stopped to think about a simple glass of salt water? It might not look like much, but you're actually looking at a tiny, invisible highway for electricity. Today, we're going to dive right into that glass and uncover the secrets of what makes things conductive.
You know, we've all been warned since we were kids, right? Don't take the toaster in the bathtub. But here's the thing. The real danger isn't just the water itself. Nope. The real story, the spark, comes from these tiny, charged particles that are hiding inside it.
So here's our roadmap. We're going to start with that initial spark. Then we'll meet the all-stars of this whole show, the ions. After that, we'll look at how we actually measure what they're doing, we'll put them to the test, and finally, we'll see why this little concept has such a huge impact on our world.
All right, first things first. Let's get right to the heart of it. What is actually happening that allows electricity to flow through a solution in the first place?
Well, it all boils down to one word: conductivity. And here's the absolute key to it all. It's not the water molecules doing the heavy lifting. It's the movement of these charged particles called ions. You can think of them like tiny little couriers, carrying an electrical charge from one spot to another.
And these little couriers, they come in two distinct teams. On one side, you've got the cations. They have a positive charge, and they're all marching toward the negative electrode. And on the other side, you've got the anions, with a negative charge heading in the exact opposite direction. It's this perfectly coordinated two-way traffic that actually creates the electrical current. Pretty cool, huh?
Okay, so if ions are the couriers, where do they come from? Let's meet the substances that are responsible for releasing these all-star players into the water. They're unleashed by something called an electrolyte. So when you dissolve an electrolyte, like plain old table salt, in water, it basically breaks apart and sets its ions free. And that is what unlocks a solution's ability to conduct electricity.
But get this, not all electrolytes play the same way. You've got your strong electrolytes, like hydrochloric acid. Think of a bursting dam. They break apart completely, releasing a flood of ions. Then you have weak electrolytes, like the acetic acid you find in vinegar. They're more like a leaky faucet, you know? Just a slow drip, releasing only a few ions. And it's pretty simple. More ions in the water means higher conductivity.
Now this is where it gets really fascinating. It turns out that even the individual ions themselves have different skills. Think of this table here as a sort of power ranking. It shows us that some ions are just naturally better and way faster at carrying a charge than others.
And right at the top of the leaderboard, we have our undisputed MVP, the hydrogen ion, H+. Just look at that number, 350. It is the absolute supercar of the ion world, just zipping through the water and carrying a charge way more efficiently than anything else on the list. It's just a brilliant illustration of how specialized these tiny particles are.
Okay, so we know what conductivity is, and we know who the key players are. But how do we actually measure this invisible property? How can we see what these ions are up to?
For that, we use a special tool called a conductometer. You can think of this device as our window into that ionic world. It measures the electrical conductivity, and in doing so, it tells us exactly how busy that invisible highway of ions really is.
All right, time to head into the lab. We are going to put all this theory into practice with a really simple dilution test. We're going to see for ourselves what happens to conductivity when we start changing the concentration of our ions.
So the procedure here is super straightforward. We start with a basic sodium chloride solution and measure its conductivity. Then, step 2, we dilute it just a bit by adding some pure deionized water, and we measure it again. We just keep repeating that process. Add more water, record the results. Simple. And here's what the data shows us. You'll notice every single time we add more water, that concentration number goes down. The ions get more and more spread out. And because they're farther apart, there are fewer of them available to carry that current between the conductometer's electrodes. So the experiment proves it, plain as day. There is a direct, measurable relationship. Lower concentration means lower conductivity. Okay, so that was a neat little lab experiment. But let's be real. What's the point? Why does measuring the secret life of these ions actually matter out here in the real world? Well, it turns out it matters a whole lot. This one simple measurement is used practically everywhere. It's how labs check the purity of water because really pure water is a terrible conductor. It's a critical quality control check in all sorts of industries. Chemists use it to pinpoint the exact end of a chemical reaction, and environmental scientists rely on it to monitor the health of our rivers and lakes. Seriously, from medicine to manufacturing, we are constantly reading the current. So the next time you see a glass of water, maybe you'll remember the bustling, invisible world that's going on inside. It's an amazing reminder that a simple principle, measured with a simple tool, can unlock applications that literally shape our entire world. And it really makes you wonder, right? If simple ions hold this much power, what other invisible forces are just out there, waiting for us to measure them?